Welcome back to the final session on application of beta diversity frameworks. And now we will look at how to use community-based data and trait data to classify species into different functional groups. So this in front of you is the RStudio console, the environment with which we are familiar by now, where we did some basic beta diversity analysis. We looked at how to calculate species contribution to beta diversity. Now we will look at how to use trait data and classify species into functional groups. Before that, let me show you how a trait data looks like. As I had shown you before in the previous session, this is how the trait data looks like. You have the various species which are coded. You have some of the continuous variables here. You have different measurements which are presented over here. These are continuous, and the others are discrete, which are mentioned here. You have diets, nesting, polymorphism, spine, so on and so forth, and all of these are coded, and these codes follow international guidelines about morphometric data, which is specifically available for ants, but different groups have different global standards. So you could follow those global standards based on what organism or what model system you are interested in. So this is broadly how the trait data set looks like for ants. You have the categorical and the continuous data sets which are inputted. So I go back to my RStudio console, and just like before, I will, in the line number 45, first load the trait data set. I run this code and the select file option is here. So I choose my file morpho_goa survey. So that is loaded. So you can see that on the global environment, the file has come. There are 68 observations, 17 variables. But what is very important to do is to clean this data. As I said, when we input information in Excel, the format of the data would vary. So it is very important to clean the data. But before that, I need to know the structure of data. So I will say str with the structure of my data mo.mas, and I run this, and I see that most of my variables of interest are classified as characters. They're all classified as characters, but I would want them to be classified as factors. I want all the categorical variables, which includes polymorphism, nesting site, diet, foraging, invasiveness, sculpturing, color of head, thorax, and abdomen. All of these, I want all of them to be classified as factors. So it's very important to look at the structure, and one by one I classify all of these as factors. And just to double check that they have been converted into factors, I again look at the structure, and I see that more or less all that I want have now been converted into factors. So this is what I want. So all of them have been converted into factor. So the last thing that I need is I want to specify row names. So I will say that the row names of this data file should be the same as that of the species that they represent. So I specify the row names, and I can open the file and check, and I can see that the row names are now names of species. So this is exactly what I would want. And then we would want to do the functional group classification, for which we would use a package called distance-based functional diversity, DBFD. However, in my case, I have edited this package, which is available for download from the CRAN network. If you would want to download the original package, you could click on packages here, click on install here. You can type DBFD. So you can see that the DBFD is not available on the CRAN package directly. However, it is synchronized within the larger package of vegan, and specifically within the FD package. So if you'd want to directly download the DBFD, use the DBFD function, You go into the install, you install the package FD here, functional diversity, and you install this package. It's already installed in mine, so I'm not going to go ahead with that. So once you have installed the FD package, you can use the base distance-based functional diversity function. However, in my case, I wanted to use a specific portion of the DBFD which I have edited within, so that I would use just the distance-based matrix out of the DBFD and use it in a HClus as a HClus data. For that, I have a custom function written here, which I would be providing you as a worksheet separately. And similarly, I want to create a custom dendrogram function within which I would want to represent my dendrogram as a circular dendrogram rather than a straight dendrogram, because it looks much better. So I have written a custom function for that. I will make that as well available. I have certain functions for the labels and certain functions for the actual dendrogram. And then I would use the ggplot wrapper for the dendrogram. So I will load the library ggdendro, and I will load the library fd to call for some of those innate functions. Then I get into the actual functional group analysis, where it is an iteration based analysis, and it can take any kind of iteration, and the start point can be random. However, I don't want the start point to be random, because I want the start point to be set. I want the results to be repeatable and replicable all the time. Hence, I will set the seed at 999. You can select any value. It's just a random value. So I have selected the seed as 999. I set this value, and then if you look at this piece of code, you can see that dbfd underscore pro is the edited custom function, and I provide two inputs. The first input is the trait data. So I have just selected that. I run that, and I can show you that I have selected the trait data. I selected all the trait data that we have worked on. We have converted all of them into factors. This is the trait data, and the pom.goa, this is the community data. Again, when I run this, I can show you that this is the community data, site species matrix. So here I have input in two matrices. One is the trait data, so species trait matrix. The other one is a species site matrix. So these are the two inputs. I don't want any corrections to be done. I want it to calculate a figure for me to take a look at what it is. I want the clustering type to be Ward's method, and I'm going to use the Gauss distance to do this, because as I had said in the previous session, Gauss distance is very good method of finding distances between two objects, where it can combine categorical and continuous variables. So based on this, I run my data, and as you can see, immediately on the right hand side, the cluster dendrogram has been drawn, and it is asking me whether I want to cut this dendrogram in terms of height or the number of groups. Since I do not have a predetermined hypothesis about how many groups I would expect, I would cut this dendrogram for height, and I have selected it based on the height from the literature. So first I would give input as h for height, and then at what height it wants it to be cut. So less than equal to 1. This is what was the basic cutoff that I had selected based on literature on ants. So I select 1 as the factor, and then it runs, and immediately you see that it has run and it has done the analysis. So a new a list of item in the name of ZDKM1 has been formed, and it has several things within that. It's a list with 13 different objects, but I don't want these 13 different objects. As you can see on the right, I don't want all these 13 different objects to be represented here. I am only interested at species functional group. So I select the species functional group, and if I look at the functional groups here, I will now see that all my species here have been classified into various functional groups, and I can see there are 8 different functional groups here, but I want the column names to be changed, so I give it a custom column name, And again, if I view, I'll see that on the left hand side I have all the species names in quotes, and on the right hand side these are the functional group classifications. So Tapinoma indicum is functional group 1, Melanocephalum is number 1, Technomyrmex albiceps is number 1. It makes complete sense. Most of the Tapinoma and Technomyrmex are in group number 1. Anoplolepis gracilepis is group number 1. These are all species which are invasive in nature. Then you have the Anictus, Dorilus, Usiria. All of these underground subterranean species are classified as one groups. All Campanotinae species are in group number 3. So this grouping makes sense to me. Overall, all the fidols are together, so this makes a lot of sense. So from this, we also cross-check and see that the function has done a fairly good job. The next thing is to now make a visual functional group tree for which we had written a custom function. So we extract the distance matrix. We want the cluster to follow the wards method. You will note that the wards method has been renamed into ward.d, and you can maybe use ward.d here, but I continue with using the old name because I'm more familiar with that. And I know that there are 8 groups from the iteration based classification. So I'm asking the dendrogram data function to classify the hclust object into 8 groups. So I run that and I do the configuration. I also am specifying certain colors under the Viridis scheme so that they are colorblind friendly. It's very important to make sure that inclusiveness is there even in our research and publication. So it's very important to have colorblind friendly colors under the Viridis package. So I specify those colors as well. And finally, I run the program to generate the cluster dendrogram. And if I zoom and show you, that's how it looks. The 8 groups are distributed and they are classified, and we have these 8 groups very neatly classified. We have 1, 2, 3, 4, 5, 6, 7, and 8 groups, and all these 8 groups make a lot of sense in terms of how they are classified. All the invasive species or species which would tend to have invasive characters are grouped together. All the seed eaters are classified together. All the subterranean species are classified together. So more or less this satisfies our line of thought, and this would be then useful for doing further analysis in terms of functional beta diversity and be used for functional redundancy. So this is the start point, and the objective of this session was to give you insights about the introduction on using community-based data, the tools which are available on open source to be used for classification of data into in terms of community ecology data, how you can use beta diversity frameworks for doing research which have conservation implications. So this was a peek or a window to a very vast and broad subject that is in front of you. I hope you would make use of these sessions to further your research and have a fresh perspective to community ecology research, move slightly further from inventory based research, inventory diversity based research, move further from alpha and gamma diversity based analysis into the realm of beta diversity analysis, and making use of these kinds of frameworks for conservation based research and conservation implication based research. So I hope you have found the session useful. I thank everyone for being patient in listening to me. Thanks a lot.